Yeah, hello and welcome to the PML School. Today we have another session where we demonstrate how to translate NONMEM models to Phoenix models, Phoenix NLME models. And the model that we have today is not too complex. It is a one-compartment IV bolus model with nonlinear elimination. So we will use the Michaelis-Menten equation to express the clearance. I think the most interesting topic of today's presentation is this, that we start with model validation. We've received feedback from users who asked for showing us how to do that, how to do validation for the NONMEM model and the NLME model, and that's what we're going to show today. There's two ways how you can validate your model, two typical ways, there are more than two, two typical ways to validate your model, and the one is bootstrapping, that's what we showed today. And the other validation method is visual predictive check, and that will be part of our next lecture in 2 weeks' time. But before we start, let me reiterate that the sessions here in the PML School are really hands-on sessions, so we are not able to cover all the theoretical aspects of model validation. If you're interested in that, I strongly recommend you look at the offerings of our Certara University. There you will find several on-demand and classroom courses that cover those aspects. I will show you a link to this at the end of the presentation. And also, while I'm going through the presentation in the next minutes, if you have any comments or questions, please use the Q&A panel at the right-hand side of the WebEx console. Moving on. So this is the agenda for today. Typically, we start with a brief model description. Then we look at the first profiles and doing an exploratory analysis. And then, as usual, we compare the input data for the NONMEM and the NLME model. The main part consists of the detailed comparisons of the individual codes, the NM-TRAN code for NONMEM and the PML code for Phoenix NLME. This is then followed by a first demo. I'll show you in Phoenix what you need to do. And then further on, I will explain the user interfaces in Phoenix to run Bootstrap for NONMEM and Phoenix NLME model, followed by another session, another demonstration, and then I will end with a summary and we can go into Q&A. So what is our model? It's one compartment model with IV bolus dose, and there we have 3 cohorts with increasing dose amounts from 1 to 10 and 100 dose units. And as I mentioned, we have nonlinear kinetics with regards to the elimination. With the parametrization, we have 3 structural parameters: V, the volume of distribution; Vmax, the maximum elimination rate; and Km, the half saturation rate constant. Let me show if I can get laser pointer. Yeah, this way. Yeah. We will apply a multiplicative residual error model with 10% CV, and we assume that all the structural parameters are log normally distributed. For the initial estimates and the fixed effects, we are setting the typical value for volume and Km to 1 and for Vmax to 5. For the between subject variabilities, we will set the random effects all to 0.01, which means 10% population variability. As the engine, we are using the FOC ELS method. moving on, this is now the first 3 profiles from the data set. There's 300 subjects and 3 cohorts, in 3 cohorts. And here you can see, starting with a lower dose, medium dose, and high dose, that from between low dose and medium dose, you see that the elimination decreases, and this shows you a nonlinear elimination, which justifies our choice for the model that I've described in the previous slide. Moving on, so these are the input data for the 2 models, and they look much the same. It's really just the column headers, and we have become familiar with those changes. So the ID column is called CID for NONMEM, an ID for NLME. DV, the dependent variable in NONMEM, is called COBS, concentration observed in NLME. We have the dosing amounts, AMT in NLME, and A1 for an IV bolus dose in NLME. One additional column we have in NONMEM is the CMT, the compartment column, which shows or indicates in which compartment the dose is being applied to which compartment, and in this case it's one. There's just one. We also have the MDV column. This is a missing data variable. It's a logical variable where MDV stands for consider this observation, and whenever there's a 1, omit this observation. And this is present in both input data sets. Okay, so this is input data. Now let's go through the model code line by line. Starting with the model selection, and here you see on the NONMEM side 1 compartment, the NComp equals 1, which is a central compartment. And in the section below, we are choosing a differential equation model, and the equation is given here. And for this, we are choosing a subroutine advan 6 tol 6, where advan 6 is a standard solver for differential equations in NONMEM, and a tolerance of 6 is pretty common and is the value chosen for the precision of the solution. Corresponding statements on the NLME model, we have to specify the dose point in NLME. This is A1, and this is a differential equation given in the deriv statement. Okay, next part of the code is definition of the structural parameters. Here on the NONMEM side, you see these are mixed with specification also of the theta values, theta, so typical values. But the structural parameters here, V is given here with inclusion of the random effect in an exponential, in a product way with the exponentiated random effect eta. And this is the corresponding statements in NLME are the ST-PALM statements, where you just put in the same equation as in NONMEM. Okay, then the next slide is the theta and omega tables. And these are just in indexed order. So theta 1 is a typical value of for volume. And in this parenthesis, you have the initial boundary and the initial estimate, and there's no upper boundary. It's a lower boundary and the upper boundary, sorry. And the same for theta 2, which is a typical value for Km, and theta 3, typical value for Vmax. Corresponding statements in NLME are fix F, where you just specify the same kind of information also in kind of vector format. We don't give a lower boundary for 0. We just put a 1 in as an initial estimate. And for the omega table, which defines the between subject variabilities, we are using 3 random effects. We've seen that in the definition of the structural parameters. Again, this is an index or order. Eta 1 is for the random effect on volume, eta 2 for the same for km, and eta 3 for Vmax. All to 0.1, and in the NLME we are using the RANEF statement that specifies the random effects and their covariance structure. In this case, we're using a diagonal structure, meaning that there should be no covariances considered. Moving on, this is the final part of the code. So the specification of the residual error model, and here for the sigma matrix in NONMEM, we specify 0.1 as the error, and corresponding statement in NLME is the error statement, where we specify a value of 0.1. The difference being this is expressed as a variance, and this is expressed as standard deviation. The error term itself is here. It's a multiplicative error model, and the corresponding NLME code uses the observe statement, where you see a similar kind of equation. And finally, for comparing the results, the output from the different NONMEM and NLME models, I just need to specify IVA as time, IPRED as F, and the individual residual is dV minus IPRED. So this is then used to create a residual table output that we can then compare with the NLME part. That's it. That's a comparison of the code. As I said, not too complex. How do you set up this same identical model with using the Phoenix interface, Phoenix model interface? So in this case, for this simple model, you don't need to write any code. You just use the built-in options, and this is shown in the this panel here. So these are most of the settings in this panel stays the same as a default. The only thing we need to change is here. There's a tick box next to saturating under clearance, so we need to tick mark this one to change the code so that it really uses the Michaelis-Menten equation. You see the code right away here on the right-hand side. And the other thing we need to change is the residual error model, where we change from additive to multiplicative. And that's it. With that, you have exactly this model. Here below is just a graphical representation of the same model. And next to it, there's actually the PML code, the textual model, which we just discussed compared with the NM code from the NONMEM model. And these are just three alternative representations of the very same model. I guess that's it so far. Let's switch to the demo. And this is Phoenix. Cheryl, can you just tell me, can you see this application? Yes. Okay. Yes. Good. Thank you. So this is now in Phoenix, and we I prepared this up front, but we can have a look. Here's under the data, we have the two input data sets. This is for Phoenix NLME, and this is for NONMEM. And this is just the same as we looked at on the slides. We have the code. The NM code is an ASCII code that is here, and we went through all the individual items here through the slides. And what you need to do in order to set up the models, for example, you pick the NONMEM data set and you just send it to a NONMEM object, NONMEM shell. I'll just put it into the main workflow, and then it will appear somewhere at the bottom here. So this is the interface to NONMEM, and you have just added the data set. There's an output folder ctemp, where all the results are written, and we just need to link the control file, that nmtran file, and for this we just drag it over like this, and then you can just submit. You can just run your model, and it will return back the results. And this looks then like this. Here you have the same setup, the data set, and the control file. Everything much the same, just with the results. Got a bunch of files loaded back into Phoenix, a main table at theta, obviously. We've got the final parameter estimates, the standard errors, and we've got the omega table and the residuals. And this we can then compare with the Phoenix NLME model. And for the Phoenix NLME model, we go back to the data, and we link this with the Phoenix model object, like we did before for the NONMEM part. Okay, this is the interface. As I showed you, these are the default settings in the bottom panel. We just need to switch to saturating, the clearance, and we switch to multiplicative. And then you see it's much the same as you go to graphical. You see this is one compartmental model with nonlinear elimination, and we can also switch to textual model, this case here, and this is a code that we've seen. I mean, there's something we don't need, like the urine compartment, because we don't have any measurements there. We don't need these variables, because these are just for definition of secondary parameters, if you want. Maybe we can just switch these random effects to the values we wanted to set it to, right? 0.1, and that's it. And then we just simply run it. Also, this one is obviously prepared, so we go in here, and you see the same setup. This is the model. Okay, 0.01, yeah. And this is the results, where you can see theta table, the estimates, standard errors, and so forth. And the same for the omega table, and lots of plots. These two model outcomes, the results, can be compared, and I've shown this several times already. We've prepared a workflow for the comparison of the NONMEM and Phoenix NLME model shown here. So we link all the inputs from the models, and then we'll do special steps to prepare a side-by-side eta values, residual values. From the residuals, we can create plots. We can create the omega table, overall table, and theta table side by side, and that is done here. Obviously, this is already prepared, so when we look at theta, this is the comparison. So we've got the three parameters, CV, Km, Bmax, and V. These are the NONMEM estimates with their standard errors, and these are the NLME errors, estimates with their errors. And you see it's pretty close. We can also look at plots. For example, the conditional weighted residual histogram looks familiar. The eta histogram looks familiar. We've got obviously the fitted curves, the fitted points here look very similar, but we won't need to look at the lattice one by one to actually see the comparison. And here you see those. They are pretty much the same. Okay, so this is the comparison between the two models. And as you know, I'm uploading all this stuff, the project file, to our forum so that you can pick it up from there and look at this in more detail if you want. So this is the end of the first presentation, demonstration. So let's go back to the slides. now coming to the Bootstrap method. This is a validation method, and it is about the goal here is to determine the confidence intervals for this model, for this final model, and then it's a simulation of a statistical sampling procedure where we create many new data sets, typically 1,000. And these new data sets are of the same size as the original data set. So it should be really resemble the same features as the original data set. But the sampling is done by randomly selecting rows from the input, and you are allowed to select a particular row more than one time. So the composition of the so-called bootstrap samples will be different. And for each of those 1,000 bootstrap samples, you fit the model to each of these data sets, and then you summarize the variability of the resulting parameter estimates. And what you would want to see, from the outcome of the bootstrap, that there's only a small difference between the parameters that you have calculated from the original data set versus the average of the calculated parameters from the many bootstrap samples. And what you typically compare is you show the original parameter estimates on one side, and on the other side you show the 90 or 95% confidence intervals of the bootstrap samples, and the original parameter estimate should lie very well within those confidence interval limits. So this is what we are using for bootstrapping the NONMEM model. We are using a software called PSN. PSN stands for Perl Speaks NONMEM. And this is a special installation of Perl, the scripting language. And this, it comes with a set of prepared Perl scripts that will execute complex protocols to run with NONMEM. And this can it covers a lot of tasks that you see at the bottom here, and one of those tasks is actually the bootstrap task. So we just use this interface to PSN and Phoenix to set up the bootstrap run. So you have to specify your input data set as usual, and you have to pick some commands. I will show you that in the demo, and then just run it. And the results, once it's finished, are then fed back into Phoenix, and then there you can compare it with the results from your original final model, or you can compare it with results from a bootstrap of a Phoenix and NLME model. Okay, then let's move on. This is the setup for the bootstrap run for a Phoenix model. What you need to do is you just copy and paste the final Phoenix model object and paste it back to the workflow of your project. And there you have to change one thing, and that is under run options. You just switch from the simple run mode to the bootstrap run mode. And the only thing you have to change here after that is you have to specify the number of samples. And as I said, 1,000 is a good value for that. So it creates 1,000 data sets from the original data set. There's also a variable for max tries. That means when once a particular model fit fails, it will just try a second time. Okay, and that's more or less the setup of the bootstrap for the Phoenix model. With that, I guess, oh yeah, we can go into the next demo. Okay. So here we are back in Phoenix, and here what we want to do is we want to set up a PSN shell. So we just need to insert from the options a PSN shell. This is shown here. You just say, okay, this is my PSN shell. I don't want to have it here, no. I just wanted to have it in the main workflow. PSN shell. What you have here, you can see, you can select sources from the Phoenix project. This is one option, and you just specify the code. And here I've got a second choice of a code, and I'll explain the differences. The only change that I did, this is the original code that we discussed in the slides. I just commented out the output tables. For Bootstrap runs, you are just interested in the parameter estimates. Any additional outputs you're not interested in, so I just commented out in order not to waste too much disk space. Okay, this is the model file for the Bootstrap. Then we also need the data set, the input data set, from which to create all the Bootstrap samples. This is just dragged over here. And then we have to set up the command to run PSN. And it is shown here. And it's really simple. You can see here are the different options. Lots of stuff that you typically ignore. But what you need to specify is a number of samples. And I mean, here you would specify 1,000, and you add this to the command list. And this is the command. Bootstrap, name of the model, minus samples equals 1,000. And then you would just execute and it would run. Unfortunately, 1,000 model fits, that takes some time. I mean, you can parallelize. I mean, I've got 8 cores here on this machine. You can parallelize by 8 on 8 cores, but still takes a long time. So I don't want to go through this during the demo. But I've got the Bootstrap already executed here. Here you see the same setup. We've got the input data set. Here is the command line, the same. And here are the results from the Bootstrap. And the main thing you're interested in is in this worksheet, Bootstrap results, where you see diagnostic means of the parameter estimates. This looks a little bit odd with a long title. So these are the average parameter estimates from this model shown here. So these 3 values are of high interest. In addition, there are some pieces at the bottom, the percentile confidence intervals. And here we are looking at the 2.5%. Also, again, for these 3 theta values, and this 97.5 shown here. And this one we need to compare then with the original parameter estimates in order to see that the original ones lie within those confidence interval limits. And also we can compare it with the Phoenix and NLME Bootstrap run. And this we can simply do by, as I said, we are just copying the final model, this one, where we got the results already. Should be there, is it? No, we didn't run it. Okay, we did this one actually. So here we've got the results, so we copy this one and paste it back to the workflow. Let's call this, boot. And what you always need to do when you reuse a Phoenix model object file, you need to make sure you take over the final results, the final estimates for fixed and random effects. That's done this way. And then you change the run options, this run mode from simple to Bootstrap, where you specify 1,000. And then you would execute and run it, and this would also run for a while. So that's why I did it already here. And here again, the main table is boot zeta, where you have the averages of the parameter estimates, standard errors, CV%, and the confidence interval limits. And those we need to compare side by side with the original model results and the NONMEM results. Okay, this is, as I said, I mean, a hands-on session. This is how you would do it in Phoenix, and you will get this project file that you can look at how each individual step was set up and run, and what kind of results you can expect, and what you can do in order to compare these results. Okay, then stop sharing this application and moving on. So these are the results from the Bootstrap. This is from our original models, the theta table, the NONMEM estimates and standard errors, and then NLME estimates and standard errors. And as you see, pretty close, just very small differences. So this needs to be then be compared with, for example, the Bootstrap theta from NONMEM. The mean values is for V is very close. KM 948 compared to 943 is not too bad. 4945, 493 is also not too bad. And these are well within the confidence interval limits. The same for NLME. Here again, very close values, and also well within the confidence interval limits. And if you compare these two tables, these are all pretty. These are also both very close. So no, they're just only small differences. Okay, this is already close to the end of the presentation. So what we did today, we set up and run a NONMEM model, one compartment IV bolus with nonlinear elimination. And we did the same for the Phoenix NLME, so side-by-side comparison, and then we processed all the results and compared them, and we could only inspect small differences. Then we ran the model validation. For NONMEM, we have been using the PSN software, and for Phoenix, the actual Phoenix model object, and compared the results there as well, and only found small differences. I guess with that, I guess I'm at the end, and we can move to Q&A. Let's have a look. Q&A. There's one question here from, what is the next step if the number of tries in Bootstrap fails? Let's see if I can move this up again. Does it mean the model is not correct? No, this can happen, and it will show as a failure. So you won't have 1,000 results at the end to run the statistics on, but maybe 990 or 980 or whatever. This can happen, and it shows you that some composition of the Bootstrap samples are a little bit far off, and so you don't get a model for that. It's just a good indication. You would need to look at the individual composition to see what is it that makes it a failure. Next question is how to perform a Monte Carlo simulation in Phoenix. Yeah, that's actually something that we will deal with in our next session in 2 weeks' time. This is a visual predictive check, and this is a simulation that's Monte Carlo, actually a Monte Carlo simulation. So we will go into more detail in 2 weeks' time. Today we just started with a model validation. Bootstrap is also very important if you sometimes if you don't have a very stable or robust model, you know, you will not get standard errors calculated for your final parameter estimates. If that's the case, the only chance to get confidence intervals is actually to run Bootstrap on those, to get an idea of you know, what is the variability on those estimates. So this is used in several circumstances. I guess there are no more questions right now, so let's bring this to the final slides. As I mentioned at the very beginning, you know, we can't really cope with theoretical aspects of model validation, but we have Certara University. They are offering on-demand and classroom courses, and as you see here, there are several courses around population modeling using NLME, and there you will learn more about bootstrapping, Monte Carlo simulation, visual predictive checks, and so forth. And you just need to go to this link, www.certarauniversity.com, where you find more information. Coming up, as mentioned several times today, next session on May 3rd, I'm showing a mixed absorption model, and here using this model I also would like to show you the validation method VPC, the visual predictive check, once for NONMEM, where we again use PSN software, and for NLME we are using the Phoenix model object. With that, I'm at the end. Thank you all for attending and for your continued interest, and hope to see you in 2 weeks' time. And with that, I want to close. You may want to disconnect now. Thank you.